Now, let's consider some more examples of applying the pigeonhole principle. But before we do that, I just want to mention a couple of important points. When we're applying the pigeonhole principle, first thing we have to consider is what are our sets A and B representing the pigeons and the pigeonholes respectively. Then we have to consider what is our function mapping the elements of the set A into the set B. And then we have to make sure that the size of the set A is greater than the set B in order to apply the pigeonhole principle. Let's consider a pigeonhole principle practice problem. There are n people at a party, and we want to show that 2 guests must have the same number of friends at the party. So it should be at least 2 guests have the same number of friends at the party. And in this example, friendship is symmetric. So if Alice is friends with Bob, Bob is friends with Alice. Okay, now when we do this, we want to think about what would be our set A and our set B representing the pigeons and the hole. So for our set A is going to be the n people at the party. And our set B we have to think about. And oftentimes the set B, the pigeonholes, are going to be has to do with the claim that we're trying to show. So we're trying to show that at least, so this should be at least 2 guests must have the same number of friends at the party. And in this case, B would be maybe the number of friends a guest has at the party. Okay, so now we have to think about this. So we know that there are n people at the party. So we know the cardinality of A is going to be n. And we have to think about the cardinality of B. And also we have to think of our function f going from A to B is going to be a function that, given a guest, maps that person to the number of friends at the party. Okay, so a person could have no friends at the party, and we don't consider someone to be friends with him or herself. So if somebody has no friends at the party, that means someone else cannot be friends with everybody else. So if somebody, so there's 2 extremes. So somebody has no friends, or somebody is friends with everybody else, n-1. But we want to convince ourselves that these 2 situations are mutually exclusive. And what I mean by that is that if somebody has no friends, it's not possible for somebody to have n-1 friend. So in that case, if somebody at the party has no friends, then the most that somebody else can have is n-2. Similarly, if somebody has n-1 friends, that means everybody else at the party has to have at least one friend, because they're friends with the person who is friends with everybody else. So what we can see from this is that we only have 2 possible ranges of value. So either we have someone at the party with no friends whatsoever, and in that case, the most number of friends that everyone else can have is n-2, or everybody at the party has at least 1 friend, and somebody else could possibly be friends with everybody else. But you'll notice that the number of friends that is possible for people to have now is either from 0 to n-2 friends, or from 1 to n-1 friends. And in either case, what this means is that the cardinality of the number of friends a guest has at the party is going to be n-1. So it's either going to be values between 0 to n-2 or 1 to n minus 1. But in either case, we're fine. We have what we need to prove this claim and use the pigeonhole principle, because we have our set A, our party guest road pigeons. Our holes, B, are just the number of friends that a guest has, which will be either 0 to n minus 2 or 1 to n minus 1. And since this number of guests is going to be greater than the range of the number of friends that people can have at the party, by the pigeonhole principle, at least 2 guests have the same number of friends. Okay, let's look at another example. Now, for this pigeonhole practice problem, we have the set of integers 3 through 12, and we want to show that any subset of 6 distinct integers from S must contain at least 2 integers whose sum is 15. So now we want to think about our pigeons and our pigeonhole. So let's see. So what is our A going to be? Let A, I think A should be the subset of 6 distinct integers from S. And we're just given that the cardinality of that is 6. But now we have to think about what our holes are going to be, our set B, our pigeonholes. And we have to construct our pigeonholes, or figure out what our pigeonholes are going to be, such that we can claim that at least 2 of these integers will sum to 15. So one way to think about this is we want to construct our holes to represent summing to 15. So we want to make holes, we want to arrange our holes so that if we have 2 pigeons in this hole, we know that their sum would have to be 15. Now, it's very tempting to want to control our pigeons. So a very common error in applying the pigeonhole principle will be, well, if I take the first, say, 1, 2, 3, 4, 5, 6 numbers, and that's my set A, I know that it has to have a matching number. So maybe I'll just take this 1, 2, 3, 4, 5, and I'll just stop here. If I make sure that I take those first 5 numbers, if I take anything from the other remaining numbers, then I know it's going to have to sum to 15. So that's a temptation, and that is what you don't want to do. And the reason why you don't want to do that, and this is really important with pigeonhole principle claims, is you don't control the pigeons. You don't control. It's saying that for any subset of 6 distinct integers from S, not the ones you choose, this property has to hold that at least 2 of these integers will sum to 15. So it's important when we're thinking of a pigeonhole principle problem, don't think about how you would control the pigeons, how you would control how the set A would be selected. What you do control is where you are going to be mapping this set into. So that's basically, you control the design of the pigeonholes themselves, so the set B. So we have to apply our creativity in seeing what would these pigeonholes have to be. So we want it to be such that if 2 of these numbers from the set A end up in the same hole, their sum is going to be 15. So now we can start designing our holes. So when we look at this, we can see, well, if I pair up 3 with 12, that equals 15. And I can pair up 4 and 11, and that's 15, 5, 10, 6, 9, and then 7 and 8. So I'm basically creating my pigeonholes, and if you'd like, I forgive for not using angle brackets, but I created those pairs, and if I was more precise, you can use the angle brackets for the ordered pairs. So I create my pigeonholes to be the pairs of numbers from the original set S that sum up to 15. And so I have 1, 2, 3, 4, 5 holes now. So my holes are going to be the pairs of numbers that sum up to 15. And when I look at this, I can see that the size of B is 5. So that's promising. But now we have to think about how are we going to have our function mapping A to B. So we can just say f of A is going to be the set in B such that A is equal to X, or A is equal to Y. If we had used a set notation, this would have been nicer still, because then we could just say if A is in this set. So let me just be more precise what I mean now. So just be a little bit more precise. So I'm going to say B is the set of subsets summing to 15. So then I have 3, 12, and I have 4, 11, and then I have 5, 10, and I have 6, 9, and then I have 7, 8. So this is much nicer in terms of mathematical notation. So you'll notice now I defined B to be the set of all subsets of S of size 2 such that their sum is equal to 15. And now what I can do is I can map A to this subset X such that X is in B and A is an element of this subset X. That's a nicer way to write that. So all it's saying is that if A is contained in this subset, then we map it to that hole, that pigeonhole. Okay, so now we have a clear mapping. We can see that every element in A will map to a subset in B, will map to a pigeonhole. So it's definitely a function. And now, since the number of distinct integers in A is 6, which is greater than the number of subsets of S summing to 15, of size 2 summing to 15, which is 5, by the pigeonhole principle, at least 2 integers in A must be in the same subset of, or same element is the same subset in, I'll just be more precise, subset in B, and by construction, must sum to 15. Okay, so this is another example of applying the pigeonhole principle, and you'll notice that just a little bit of precision with notation can help you. So one thing that may have seemed a bit ambiguous is that when I said in the same subset in B, so in the same subset of S in B, I should also have said that because B contains subsets of S of size 2 that sum to 15, and that is what I meant by construction. We constructed B to be all of those subsets of S of size 2 that sum to 15. Okay, let's look at another example. Now, for this example, we want to prove the claim that for any set of 9 positive integers, at least 2 share all of their prime factors less than or equal to 5. So in some respects in this problem, we're thinking about what are our pigeons and what are our holes, but in some respects our hands are tied because we're basically told what our set of pigeons are. So let A be a set of 9 positive integers. And what is very nice about this is now it makes it very clear that we have no control over our set of pigeons. These pigeons are just some 9 positive integers, and we do have to do work with our set B. And we have to figure out what our set B is. And often when we're thinking of what our pigeonholes or set B should be, we have to think about what does it mean for 2 of these integers to share their prime factors less than or equal to 5. So now let's think about it. What are the prime factors less than or equal to 5? So we know that 1 is not included, but we can have 2. So let's think we're thinking of the prime factors less than or equal to 5. So we have 2, we have 3, or we have 5. And now they have to share the same prime factors less than or equal to 5. So in some respects, it is asking us to consider what subsets of these prime factors that these integers must have. So now we can think of our set B to be the power set of all of the prime factors less than or equal to 5. So basically our B is going to be the power set of 2, 3, and 5. And just for practice, we can enumerate what this power set is. So they can have no prime factors less than or equal to 5, or just 2, or 3, or 5, or perhaps 2 and 3, or 3 and 5, or 2 and 5, or they can have all of them. Okay, so we just enumerated this power set of all the prime factors less than or equal to 5, and now we want to think about what is the size of this power set. So the size of this power set is going to be 2 to the 3, which is the cardinality of the number of prime factors less than or equal to 5, which is 8. So now we've done enough to apply the pigeonhole principle, but we have one element of care that we have to do. So our function going from A to B will take an integer in the set A and map it to its subset of prime factors less than or equal to 5. So that's what we're mapping. We're mapping each of the integers to that. So just to give a concrete example, so for example, if we had 7 in our set A, it would map to the empty set. But if, for example, we had the number 30, it would map to the entire set, and so forth. Okay, so now we've clearly specified our pigeons, or set A, our pigeonholes, or set B, the function from A to B, and we can see that every element in A will map to one of the subsets in the power set of the prime factors less than or equal to 5. So it definitely maps to a point in the codomain. And now, since the number of integers, positive integers, is 9, which is greater than the power set of the prime factors less than or equal to 5, which is 8, by the pigeonhole principle, at least 2 integers in A map to the same point or element in B, which is a subset of the prime factors less than or equal to 5. So basically, when we have 2 integers mapping to the same point in B, so that's the same subset of factors less than or equal to 5, or point in that power set, element in the power set, that means those 2 integers have the same prime factors less than or equal to 5.